Welcome back to linear algebra. Let's jump into Anki. State 5 results that are equivalent to the statement that n by n is a matrix. That n by n matrix A is invertible. A can be expressed as a product of elementary matrices. The reduced row echelon form of A is I. Ax equals 0 only has a trivial solution. Ax equals b for all Ax equals or for Ax equals b. B is valid. B has a solution, I should say, for every b, n by 1 b, and then or any, and then for every I say for Ax equals b, a solution, or it is every for Ax equals b, for any b n by 1 b, there's a solution, or it is consistent, and then for every b in Ax equals b, there is exactly one solution. What are the coefficient matrix and augmented matrix of a linear system Ax equals b? Coefficient matrix is A, augmented matrix is B. No, it's not. That's right, augmented matrix. Okay, that's A partition B. Come on. Let A and B be square matrices. State two equations, either of whose validity guarantees that B equals the inverse of A. AB equals I, BA equals I. What is an invertible matrix, and what is another name for such a matrix? An invertible matrix is a matrix that exists in which another matrix exists that it commutes with, and both of them equals I. Both become like the matrix times and the inverse times the matrix, and the matrix times the inverse both equal I. Such a name for another name for such a matrix is non-singular. It's a square matrix. Is it possible to multiply two invertible matrices of the same size and obtain a matrix that is not invertible? No. All right. Let's check where I left off. Oh, that's right. We have problems to grade, so I'm going to grade these. Actually, we got to learn first what the skew symmetric is, so I'll be back in a bit. All right, so I figured out what skew symmetric is. The reason I couldn't get it was because I didn't realize that the main diagonal are just zeros for a skew symmetric. That's how you do it. And then if you switch the rows and the columns, if these are like, if mirrored over the main diagonal are the negation of each other, then it will be skew symmetric. So there's that. The proof I got wrong. I'll show you where I got it wrong. So I assumed that if A times A, the transpose of A equals A, then AT equals I, because I'm like, well, I times A is how you get A, but what if these are, for example, zeros? 0 times 0 is 0. You don't need to be an identity matrix then in that case, so it doesn't have to imply I. So I wrote it. It was actually pretty simple. If the transpose of A times A equals A, then if we take the transpose of both sides and then we distribute the transpose, then we know that the transpose, or A times the transpose equals the transpose of A. So if A times the transpose equals A and A times transpose equals the transpose of A, then we know that A times the transpose of A are equal. And if the A and the transpose are equal, then A is symmetric. If A times the transpose of A is equal to A, and that A equals the transpose, then A times A equals A. That could have been written a little better. I'll just show it like that. So you're plugging in, actually that should be the other way, over here. That should be there. Actually, no, it doesn't. Like, ooh, I kind of threw these around. I should have been more careful with the order of multiplication, but it's fine. So A times the transpose of A equals A. What the heck? Why does this look backwards then? Oh, because I'm reading it backwards. There it is. A transpose is the first item here. A times A equals A, and so A times A equals A squared, or A squared equals A, I mean. And then for the 3 true or false, we got them all right. So, all right, we've got like 1 more minute, so I'll be back in a second after I try some problems for a minute. All right, just did a quick review problem from 1.3. True false. Basically, it said if AC equals BC, then A equals B. Now, false. Example: A equals a matrix of 1s, B equals a matrix of 2s, C equals a matrix of 0s. So A times C is 0, B times C is 0. They're equal, but A doesn't equal B, not C. It doesn't even say C is not 0. And there's other ways that we could have proven or disproven it, but that's easy enough for now. So that's it for today. Did we make it through? No, we have like 1 more true false, and maybe a technology problem from 1.7. I can just check right now. There's only 1 technology problem, so we don't need to do it necessarily on this pass. We can do it on the second pass. Yeah, we have 1 more true or false from 1.7, then we'll have 1 pass through of 1.7, then we'll do another second pass from 1.7. So that's it for today. Talk to you tomorrow. See you.